everybody. Today we're talking about predicting nuclear stability. We've seen a little bit about nuclear radiation, things like Chernobyl, or events like Chernobyl where nuclear radiation has been really serious and really affected us. We've seen how to write balanced nuclear equations, and now we're actually going to take a look at, well, how do we actually predict what kind of nuclear radiation or what kind of nuclear decay isotopes will undergo. So today we're predicting nuclear stability. There's a couple of different ways we're going to do this depending on what isotope we're looking at. So we're going to have a few steps for problem solving in the end. Basically, with predicting nuclear stability, we can use a neutron to proton ratio, so calculate the neutrons divided by the protons, or atomic mass, the average atomic mass that you find on the periodic table, to predict which nuclei are unstable, and then, if we determine that they are unstable, predict what type of decay they're going to undergo. So this is a process that we're going to use to predict whether isotopes are stable or not, or whether nuclei are stable or not. One of the things that we're going to be looking at is called the band of stability. And this is a region where all nuclei will fall when we graph neutrons, a number of neutrons versus a number of protons. Now this is a rough drawing of the band of stability, where you have this line going up, and this is a reference line where the neutrons divided by the protons of the isotope are equal to 1. This line is a reference line that's here for us to look at to see generally where isotopes fall. So if you have an isotope that is really kind of smaller, all right, and you have a neutron to proton ratio that is less than 1, generally it's going to be electron capture. Neutron to proton ratio greater than 1, which is above the reference line, n equals 1, or n over p equals 1, it would be a beta process. And we see when we get up here to really larger nuclei, they tend to be alpha decay. And we're going to take a look at what this looks like. But what I want you to notice is that these isotopes, all of these dots are different isotopes, or representing different isotopes. They generally tend to follow this n over p equals 1 line until they don't, until they start to kind of go up a little bit. Okay, so that's going to come into play when we're predicting decay. It's nice and neat down here where we have slightly smaller isotopes, and when they start to get bigger, it gets a little more subjective. So what I have here, all nuclei outside the band of stability, so outside this band, are unstable, and they'll undergo decay. So anything outside the band, which is generally just like right through here, anything outside of that band will undergo decay, outside the center of that band. So let's look at how to predict. We're kind of applying a mathematical process here to figure out what kind of decay isotopes or nuclei will undergo. So here's our guidelines. The first thing we want to look at is, what is our proton number? So if our proton number is between 1 and 20, okay, so if you look at the periodic table, element 1 here is hydrogen, element 20 is calcium. So you have protons between 1 and 20, so hydrogen to calcium, then this is what you're going to do. You're going to calculate number of neutrons over number of protons. Okay, so you're going to actually have to put that into your calculator, calculate it, divide it out, neutrons over protons, and see what you get. If you get neutrons and protons are equal to 1, then this is a stable isotope, a stable nuclei. And that's where it's going to fall right on this line down here, because the neutron to proton ratio is going to be equal to 1. If you find that the neutron to proton ratio is greater than 1, which means it's going to lie up here, that means there's too many neutrons. Okay, so if it's greater than 1, we predict beta decay, because it has too many neutrons. It has too many neutrons, okay? So it's going to give off an electron, and the resultant product is going to have an extra proton, right? So you're getting closer to a neutron to proton ratio over 1 by decaying under beta decay there. If the neutron to proton ratio is less than 1, so down here below this line, below the reference line of n over p equals 1, that means that you have too many protons. If you have too many protons, then your nucleus is going to capture an electron so that it can ultimately, the new product will have one less proton. which again brings your neutron to proton ratio closer to N over P equals 1. That's the goal of these nuclei, are to become more stable. Now, if your proton number is not between 1 and 20, but it's greater than 82, well, that's an easy one. We're going to predict alpha decay. So greater than 82, we've already seen this element. Okay, if you're looking at the periodic table, you want to find atomic number 82, which is lead. We've seen lead when studying stars and how elements are formed, right? Lead is formed in the core of stars, and it's the largest element that can be formed in those stars while they're forming. So if that proton number is greater than lead, it's alpha, because these are too big. The nuclei are too big, and they want to get as small as possible, as fast as possible. The easiest way to do that is to give off the biggest decay particle, which is an alpha particle, a helium nucleus, 4 over 2 He. Okay, remember, 4 over 2, well, not a fraction, 4 over 2 He is our helium nucleus that it's going to give off in that decay. Now, if you have a proton number that's neither between 1 and 20, it's also not bigger than 82, that means it's between 21 and 81. If that's the case, then instead of calculating the neutron to proton ratio, you're going to look at the mass number, A, over the average atomic mass. Now, the reason I put A there is, remember our nuclear notation, A over Z X, where Z is the proton number, A is the mass number. So you're going to calculate mass number over average atomic mass. And it might help for you to write in mass number right here. So you remember A, or mass number, divided by the average atomic mass. If that number comes out to be greater than 1, just like up here, greater than 1, it's beta, okay? Because it's still going to be above the band of stability, the band where everything is stable. So it's going to be on the higher end. If that mass number over the average atomic mass is less than 1, then it's going to be electron capture, just like it is up here. Neutron to proton ratio less than 1, electron capture. And that's because it's going to lie at the low end of the band of stability because there's too many protons. Okay, so let's look what that practice would kind of look like. You're going to see this on the isotope browser lab that you're doing in class. So here we have the steps. And I'm going to walk you through each of these steps for all of these isotopes in all these nuclei in our table. So we have magnesium 21, and I put here the number of protons. You can find that on the periodic table, but I wanted to make it easy and quick. So we have 12 protons. So the first thing you do is look at, is Z greater than 82? No, 12 is not greater than 82. So we know it's not alpha. If yes, it's alpha. If no, go to step 2. So we're going to step 2. Is Z between 1 and 20? Proton number 12. Yes, it's between 1 and 20. Then we're going to calculate the neutron to proton ratio. Now, just to make it easy, our neutrons over here, remember the mass number minus the protons, and that's going to give you 9 neutrons, okay? We can write our nuclear symbol here. So we have 21 over 12 magnesium. That's our nuclear symbol. We need to figure out what kind of decay process do we think it's going to undergo. Well, we need to calculate the neutron to proton ratio. So my neutrons here, N over P is equal to 9 neutrons over 12 protons. And when you calculate that out, you get 0.75. Okay? Well, what are we going to predict then? Neutron to proton ratio is less than 1. Neutron to proton ratio is less than 1. So we're going to predict electron capture here, because it's going to lie on the bottom end of that band of stability. Our balanced nuclear equation then, we have 21, 12 magnesium. It's going to capture an electron. So we have an electron captured here. It's on the reactant side. And we're left with 21 as a mass number on the right. 12 minus 1 is going to give us 11. And then you look on the periodic table to find out that element number 11 is sodium. Okay? Now, the next one we're going to look at is radon-222. Step 1. Is Z greater than 82? Proton number greater than 82? Protons are 86, yes! The proton number is greater than 82. So if yes, alpha decay. So automatically, well, let me write the nuclear symbol first. We have mass number, 222, over the proton number, 86, and radon is Rn on our periodic table. The decay process prediction we're going to say is alpha, because this nucleus, the proton number is too big. It wants to decay as fast as possible. So Z is greater than 82 is our prediction. Nucleus, too big. Okay. Up here I also should have written, because N over P is less than 1, part of our justification is there's too many protons. And I'm going to put P plus for protons. Okay. Now we can write our balanced equation. We have 222, 86, Rn. It's my nuclear symbol. And we're undergoing alpha decay here. That means an alpha particle, a helium nucleus, is in the products. And 222 minus 4 will give us 218. 86 minus 2 gives us 84. And if we look on the periodic table, we see that's polonium. Okay. Now the third one, we have nitrogen 14. Is Z greater than 82? Well, proton number is 7, so no. Is Z between 1 and 20? Well, yes it is. Proton number is 7, so it's between 1 and 20. So we're going to calculate the neutron to proton ratio. So over here I'm going to do the neutrons. 14 is my mass number. 7 is my protons. So I get 7 neutrons, and with a 0. All right, so I'm going to write my nuclear symbol here. 14 over 7, N for nitrogen. Well, we need to calculate the neutron to proton ratio, so I should have done that over here in the justify prediction. So neutron to proton ratio is equal to 7 neutrons over 7 protons is equal to 1. Okay? Well, what are we going to predict? If N over P is equal to 1, that's a stable isotope. So we're going to say stable, because N over P is equal to 1. All right. If we write the decay process, right, what are we going to write? 14, 7, and that's what we're starting with. This is stable. No decay. It's not going to decay because it's stable the way it is. Remember that isotopes will decay until they become stable. If it's already stable, it has no need to decay. Okay. Now our last one, cesium-137. You can guess that we're probably going to go to step 3 for this one. So, is Z greater than 82? Well, our proton number is 55. Nope, not greater than 82. Okay, so if no, go to step 2. Is Z between 1 and 20? Proton's 55. Nope, not between 1 and 20 either. So, if no, go to step 3. All right, is Z between 21 and 81? It should be, and we see that it is. 55 is between 21 and 81. So we're going to calculate A, the mass number, over the average atomic mass from our periodic table. Okay, so let's write our nuclear symbol. We have 137 over our proton number, 55, and cesium is CS on the periodic table. Okay, let's calculate the number. Oh, no, we don't need the number of neutrons, right? Because we're not doing neutron to proton ratio. We're doing mass over average atomic mass. So for my justify over here, we need to figure out, we need to do the math. Mass number A is 137, divided by the average atomic mass. So if you look at cesium on the periodic table, you see an average atomic mass of 132.91. And when you divide that out, you get 1.03. Okay? A little bit bigger than 1. Not much, but it's a little bit bigger than 1. So we're going to predict here beta decay because it's a little bit bigger than 1. So our justification, here's the math for our justification, because too many neutrons here. Too many neutrons.